The first presenter is Professor Nick Hawes, representing the Oxford Robotics Institute. Nick is leading as a principal investigator this Oxford research program, and he will deliver a talk about the long-term and large-scale autonomy.
Thank you for the invitation to speak, and thank you for all the amazing introductions from the invited speakers beforehand. So it's a great pleasure to be here speaking on behalf of the Oxford Research Pillar within the Oxford-Singapore Human-Machine Collaboration. I'm sharing the session with a colleague from Singapore, so Professor Marcelo Ang from the Advanced Robotics Centre at NUS. I'm, as Sherolta said, representing the Oxford Robotics Institute at the University of Oxford. And we're paired up together because we both have similar interests in this question of large-scale and long-term autonomy. And our work focuses on, I'd say, enabling AI and robotics technology for human-machine collaboration, but not really the direct interaction of humans and machines, more about how we build autonomous systems that work for humans and alongside humans in a range of environments. So those are our main interests, and what we're going to talk about here is really kind of the research level work that's going on, and as is natural with robotics and autonomous systems, how this is applied in various ways as well. And they're going to be fairly brief presentations, and then we're going to have a little bit of discussion between the two of us on what we think maybe some of the open issues are. Okay, so that's the intro. I'm going to dive into my slides. I'm going to talk about my research group at the University of Oxford and how our work here is contributing towards human-machine collaboration. So my research group is called the Goal-Oriented Autonomous Long-Lived Systems Group, or the GOALS Group, and we work on decision-making techniques for autonomous systems. And we're particularly interested in autonomous systems that exist for long periods of time in their target environments and make decisions under uncertainty. So uncertainty is always present in robotics, as are typically the dynamics that are caused by human activity in the environment the robots are in. So autonomous decision-making under uncertainty is key for robust, successful, safe, responsible developments and deployments in robotics in a range of applications. And I'm going to give you some examples of particular applications that we're interested in and particular angles that we're interested in as we go through the slides. So I thought I'd start off with maybe a general approach to talking about how my group works on this topic. And we think about the world in terms of probabilities because we're worried about uncertainty, and predictions. So our systems work, oh crumbs, I'm sharing the wrong screen. There we go. I tried to, sorry. I tried to make this better and I shared the wrong screen. There we go. Right, sorry, give me a second. Right, well that's highly embarrassing. I think we're all hyped up for our level of technological prowess, then I make a rookie mistake on the sharing. I wanted to change the screen from my desktop to my laptop so I could look at you while I talked, and then I shared the wrong screen. Excellent. In my defense, it's before 7 a.m, so I'm going to apologize for that. Right, maybe in case you didn't see, that was the intro screen. Here I talked about the research of my group, and then we'll jump into the key topics of how we work. So we work with probabilistic predictions. The general idea is that when a robot acts in an environment, it performs tasks, whether that's moving from A to B, whether that's picking a package, whether that's interacting with a human. It performs those tasks repeatedly. And we can gather data. So Nigel talked eloquently about the role of data in robotics and AI. And we can use it in terms of characterizing the performance of a robot. We can capture that into some kind of probabilistic representation. And we can do the same with human behavior. So when a human's performing a task, such as picking a crate in a warehouse or servicing a car in a garage, we can model all of these things in terms of their probabilities, how successful they are, how long they take. And then we can embed these predictive probabilistic models into structures that allow us to plan for how robots and how humans should behave to best deliver successful tasks under that kind of uncertainty. And this is an approach that also, as Nigel said, mixes different technologies. We're interested both in machine learning to gather and capture these probabilities, but also more traditional plan-based and model-based AI, so hybrid systems that allow us to reason about the structure of these models and robot behavior under these kinds of uncertainty. So I'm going to talk about these techniques, so this kind of approach applied to 3 projects out of the 8 that's going on within the Oxford Singapore research pillar within the Human Machine Collaboration Initiative. And I want to say a huge thanks to Amazon Web Services, or AWS, who are very generously supporting the Oxford research pillar of this initiative. So a lot of this work now is funded or supported by them. So the first one, long-term autonomy. So I'm particularly interested, and I mentioned this at the beginning, about how we can embed service robots or robots for long periods of time, weeks or months, into human environments. And this talks about some of the work we did to deploying service robots using these approaches. The key idea here is that we were planning behavior for hours of robot behavior, planning actions for hours of robot behavior over months and months of continuous autonomy, and using techniques that provide probabilistic guarantees, so using techniques from formal methods and computer science in order to guarantee the robot behavior, even in the front of uncertainty. And this is really important because what we found when putting robots into care homes, into offices, is that they encounter all sorts of failures. And those failures prevent the robots working successfully, and they also can cause hazards or delays in operation. So what we do is we take this general approach of running the robots in these kind of environments. We capture the data for failures, such as getting stuck on chairs as they're navigating, or having to deal with cleaners leaving brushes over charging stations. And also we have to capture data around the delays that human interaction or human collaboration causes. So in this case, this is the delay of waiting for a human to open a door. And we embed these into models that we can use to plan robot behavior. Taking this approach, we deployed robots for years of autonomous behavior in a range of operations, from care, which you see down here, where we had robots working in care homes, providing assistance to nursing staff and sharing information, to security, monitoring humans in a range of situations, and office management. So all of these robots are running plan-based guaranteed controllers that use data derived from everyday interaction, where these controllers get better every day because we get more data every day. So this really shows our general approach in action. We're applying this directly into retail now, working with Bossa Nova Robotics, where we're applying our planning techniques on their shelf scanning robots. They have robots taking stock in hundreds of Walmart stores in the US, and they're trialing some in the UK. And we're looking at how we can apply these planning techniques using data gathered from operation in order to improve the efficiency and reliability of robots that they're deploying into supermarkets right now. If we move from here to logistics, increasingly companies are looking at logistics tasks where not just controlled robots are working in static environments, but where there's large-scale interaction between humans and robots. And those are very interesting application areas. So we're looking at applying these probabilistic planning techniques across teams of robots in logistics tasks, and particularly teams where the robots must respond to humans and vice versa. So this includes agriculture, that you can see in the picture here, where human pickers are filling baskets of fruit before they call a robot to collect this, and also robotics for retail and kind of distribution centers, where humans are picking crates of items and robots are carrying them off. So these are 2 areas that are being actively developed right now. And we're looking at how we can guarantee robot response times in those fleets. So imagine you can sell a customer on a guaranteed quality of service or guaranteed response time of a robot fleet under Dynamics. Those are the kind of plans we're trying to produce. So you can actually effectively promise a particular operator the level of response you get from a particular robot configuration. And this is, again, relying on this idea of collecting data under the hood and using those probabilistic models to plan robot behavior. So we're also using this idea of probabilistic models of logistics facilities to do some generative design work. So this is work joint with Accenture, who are a partner of the Oxford Robotics Institute. And they're interested in how probabilistic models of robot and human behavior can lead them to design better warehouse environments for their customers. So our process takes an existing warehouse, and this is a warehouse at Blenheim Palace down the road from Oxford. And we can go there, we can put some robots into the sites, and we can gather some data about the throughput of the robot tasks in this environment. At the same time, we can take a reality capture, a 3D scan, build various models, and compare reality to simulation before altering the simulation and running hundreds or thousands of simulations in AWS in RoboMaker to characterize a range of different environments. So the great thing about this is it allows you to try different types of environments, different types of robot configurations, and create a huge range of simulations to test future applications. But we're doing it in a way that's founded on data coming from the real world and real robotics. So this really goes beyond some of the weaknesses of current discrete event simulators for these kinds of tasks. I'm running a bit short on time, particularly because I screwed up the sharing at the start. I'm sorry about that. So I'm just going to go for one last quick overview of the last project we're working in, which is human-robot shared autonomy. So in this space, we're hugely interested in who's in control of a robot platform. So is it a human operator? Is it an AI system? The most classic example of this is whether you have a human or an AI system in control of an autonomous vehicle. But increasingly, this will be present in a huge range of high-risk or high-value applications where robots must work but cannot do all of the tasks themselves. And in these situations, you want humans to be called in for help, either to drive the robot or to train the robot. And so one of my key areas of research for the near future will be this task of shared autonomy. How can we decide when a robot asks for help and who the robot should ask for help in order to do tasks like search and rescue, which we see in the bottom left? So this is a robot searching for human survivors in a disaster zone, which happens to be a computer science building. That robot uses the human to solve problems for it, and the human can task the robot and switch the robot in various ways. In the top right, we see a human that is being called in to train a robot when a robot fails a particular physical task. And this is an area which I think will be hugely important as we increasingly deploy robots into new and challenging environments. Okay, so that's my short burst over. I'm now going to hand over to Marcelo, who's going to give a similar talk before we have a quick discussion to cover our research interests. Thank you very much.
Thank you, Nick. Get the screen up. I hope you're seeing the screen. If something's wrong with the audio screen, please let me know. So the key word is pervasive. What do I mean by that? I want to move away from industrial robotics, which is very useful, where the robot and human are separated. The robot is inside the cage. When the cage opens, the robot shuts down for safety reasons. I characterize this as structured environments, but we need to move towards pervasive robotics, that is robotics in our daily life, from structured human-robot separation to our shopping malls, our homes, hospital wards, and also in the grocery aisles, for example, where the opposing concepts is unstructured. The robot doesn't know beforehand exactly where things are. There is a clear human-robot interaction, no longer separation. And how do we do this arrow, right? To move from the left to the right, where the space is not designed for the robot, but designed for human beings, and how we can have robots to adapt to it. So we view robotics as the ultimate helper. A robot must have mobility, some wheels or legs, and must have some arm, and together with its body, a brain, but not in isolation. The human is also there as a co-worker for the robot, for the co-worker for the human or co-companion. And there are many tasks that we do every day that we will have the robot that can help us do the task with us or do the task for us, but always under our supervision, right? I call the more meaningful tasks the 5Ds: dangerous tasks, demeaning tasks, degrading, dirty. And 10 years ago, I started working on the 5th D, which is driving vehicles. These tasks are very mundane for people. People are too intelligent to do these tasks. And secondly, robots or machines potentially can be better than humans in such tasks. So the brain, I'll focus more on the brain. We do 4 things all the time. First is see the environment or sense the environment and make understanding, context awareness. After we understand what's going on, we plan. After we plan, we execute the plan and we learn. And this is happening continuously. So this loop goes on and on. And how can we have robots to have this capability for a long time so it can continuously improve? So its autonomy, its intelligence improves all the time, working better and serving humans better. So our brain, there are 2 approaches. The traditional approach is model-driven, where you use science to develop a mathematical model that relates inputs and outputs. And once you have the mathematical model, for desired output, use the model to compute the required inputs to control how our world behaves in. But we will know, I think people understand that now, that this is very hard to do. It's almost impossible because the other approach that humans perhaps do in our daily lives is data-driven approaches where we learn from experience. For example, for me to move to pick up a cup of water, I don't need to have a mathematical model of the dynamics of my hand, the weight of my hand, how my muscles actuate my hand. I just do it by trial and error. And that's the data-driven approach, right? And this is really the marvel of how our brain does it. Perhaps the best way is a hybrid approach that I think Nigel also mentioned is how to combine data, and also Nick mentioned that too, and model-driven approaches, and to use both when it is. If we have some knowledge based on science, we use it, but we know it's not accurate. How can we use data to make it more accurate? So here's some work we have done on autonomous vehicle. We call it multi-class mobility on demand. There's supposed to be some sound. I don't think it's hearing sound, but never mind. The sound is just some background music. So you call a vehicle, you want to go to the nearest train station. You get the buggy comes to your doorstep, not quite your doorstep, in the ground floor of the building in our university town. You enter the buggy, you key in your PIN to make sure you're the one who booked it, and it goes to the nearest train station, not directly because it has to go to a point where another car, another vehicle meant for the road is waiting for you. And you can see on the top here is how much far ahead the sensors are seeing. And we call this a mobility on demand using autonomous vehicles. This is running 2 times the speed. You can see the human walking. This goes through buildings because our vehicles do not use GPS because they're not reliable and they don't work indoors too. So our approach has been always the environment is built for human beings. How can the robot have its own intelligence on board so it can understand the environment and navigate through it without being told by the environment what to do? So it goes to the roadside. Scott, another vehicle that is autonomous, is named after my student Scott, also means shared computer operated transport. And this is a move of Singapore to go towards a car light society where people don't own cars, but we have a very good public transportation system. So you book, you enter your PIN and you confirm your destination and you say go, that's correct. Then the car just drives itself. We don't build the car, we don't build the golf buggy, we just modify it and put our computers and sensors to make it workable. This is a plan of Singapore in 2022 to really deploy public buses for what we call the last mile problem, to bring people from their homes or offices to the nearest train station within a 3 kilometer to 5 kilometer radius. This is a visualization of animation for Singapore bus, but using live real data from sensors during our trials in public roads in Singapore. You can see how it detects objects meaning other cars around it, and how it detects also the sidewalks and the lane boundaries and the island between the 2 lanes of the road, and how much it sees in the left and right. So autonomous vehicles can potentially be better than humans because it sees everything. Perception is certainly better. It can classify objects, but what's keeping us from moving forward is prediction. How does is really the planning of the actions based on understanding the environment, because you can understand the environment as it is, but you cannot predict what the environment will look like 1 second later, 5 seconds later, a minute later, especially if they're human-driven cars. We all know how unpredictable human behavior is, and that's really a challenge for human-robot collaboration. How do you really operate robustly even when the human or prediction are wrong, and how you improve your prediction? It's almost like us driving vehicles. How do we learn to be better drivers as we drive more vehicles, as we encounter more scenarios that we haven't seen before, and how we improve? By 2022, Singapore hopes to have these buses fully autonomous, level 5 automation, meaning no safety driver, doing the feeder service to go to the nearest train station. So pervasive robotics really mean robustness and scalable. And it's really not in isolation with humans. I call it, or we call it divided or shared intelligence, where the robot or the machine has as much intelligence as possible, so the human literally just turns it on and off, and maybe for some exception handling, and how the human and robot work together by human asking robot to do things. How does the robot ask humans for help? So it goes both ways, and to continually learn, and the robot to be, we call it a co-X, where X can be a worker, helper, companion, would be the ultimate machine for all of us. So the key challenges, I call it general intelligence. There are two main important things. One is how much data is enough that you can trust the machine to operate safely and robustly. It's almost related also to the question that Nigel brought about on trusted AI, right? There's a concept in engineering called persistently exciting trajectories. Perhaps we have to give data that are rich enough so that what you want to identify, the underlying models, will be revealed, right? In this data is somewhere buried under the data. That's first. Second is how is this data or knowledge represented? And for lack of better models, right, we just fall back on our brains and a primitive approximation of our brain, which is the deep neural networks. And what are the underlying features that are critical? We can borrow also, the dashes are borrowed from traditional engineering and scientific methods, perhaps principal component analysis, factorial analysis in design of experiments. If things are very complicated, how do you design experiments such that the underlying features that describe the true behavior of what you're trying to understand and control can be identified and revealed. So these are some of our more recent work in localization. This is a train station in Singapore, Raffles MRT. The left and right is the same station. If you use a vision system to detect, are these two images the same? Obviously it's wrong, but humans know they are the same because we know these people are temporary. So how do we localize by removing those non-permanent features of the environment? This is another approach. Rain is very hard to work for sensors to work. Our AVs do not work on rain. Can we remove the rain, right? But humans do this very nicely, right? If I see an image that is rainy, I can imagine what the image will look like without the rain. So the reality is on the left, the right is my imagination of the same scene, right? But we need a lot of data. Humans able to do that. The hypothesis is because we have lived long enough in this world. So, but generating data is very hard, right? I cannot get my students to keep watching the sky and wait for it to rain and take pictures. So we generate data synthetically through simulation. And surprisingly, by training, giving enough data to simulation, many days of rain can be simulated in hours, and we can test it on real world data. And it's really nice that it surprisingly works quite well. The left is the rainy data, the right is after processing it using our neural network to remove the real world data. So the neural network does give us examples or motivation, inspiration to do that. But still, the open question is how much data is needed for it to be generalizable so that it can operate even in places where it has not experienced before. Here I list a lot of tasks that if robots can do for us, with us, helping us, will really be an improvement in everyday robotics in making robots really work for us. And all of this, the robots cannot still do today. And here is a final video I just want to show. There's no sound, so it's harder. But it's really, maybe I'll be the sound. I'll fast forward a little bit. So the robot detects the human hand and where the hand is and just picks up the object through voice. The human says, "Give me the bottle." The robot will pick up the bottle and the robot will find the human hand and pick it up for you, right? So this is one example where we use natural dialogue to help, and we use some object detection standard methods that you only look once method for doing the post estimation of the robot. Fast forward, and we have some dialogue, and in the natural dialogue interaction, we need to understand. It's not only reading up a question and answer. Right? We need to understand the dialogue and do a sensible interaction. So that's very important also in human-robot collaboration. So thank you very much, and that's the end of my thing. And we want to spend maybe 3 or 4 minutes for questions or in discussion with Nick and I. If you have anything you want to tell, maybe I'll start with Nick if you have any comments. And I can start with I can start also with my comments. I think on your part of the talk, we see a lot of synergy, in interest,
Absolutely. I mean, when I got your slides by email this morning, I was like, wow, we think about the world in a very similar way. So I think the use of
really
kind
great.
of data plus model seems the right way. And I mean, I was really hit by your description of unstructured environments. I mean, that is the big challenge. I was wondering what you thought what is the biggest challenge of operating robots in environments with humans, in unstructured human environments.
I think the biggest challenge is predicting human behavior. How will the human react to each action the robot makes? And this can be a potentially unstable problem because my reaction depends on your reaction. Your reaction depends on my reaction. In a car situation, let's say 2 cars want to go to one lane, want to merge into lane. So either I start to speed up, the other car starts to speed up, and who will give way first? I think that is hard.
There are some lovely papers on social navigation where they evaluate techniques and the robots just get stuck. So you either become aggressive or you end up the robot just sits there and never goes anywhere. I think we, in some of our work deploying robots into offices, we ended up, I think we tended to try and get the robots to fail quickly. So if the robot couldn't act and you got into that situation, we tried to get the robot just to bail out very quickly and have some robust recovery actions, which is a lot easier to do in a wheeled indoor setting than it is on the road, for example. But it's
right. Indoor, outdoor is quite a different set of parameters. Different constraints. But you're right. Social navigation is very interesting. We want, let's say, a wheelchair that's moving around in a hospital or in a mall. You want it to be non-intrusive, and people should be very comfortable with it. And I think if the world is full of all this autonomy, it will be easier. But I think the challenge goes back to you can be aggressive or non-aggressive if you're the machine. But if it's a human there, you cannot control the behavior of the human.
No. I mean, what I find interesting as well, and we'll both have to deal with this in various ways, is that robots or autonomous machines are held to very different standards in terms of their behavior than humans. So we had in the care home, we had a situation where one of our mobile robots got close to someone on crutches, and that caused a big fuss because it could have been dangerous. But what you see is that humans are walking and bumping people on crutches.
Much closer, right?
People on crutches are hitting other humans just every day. It's just everyday interactions. But when you have a robot acting in the same space as a human, they get treated very differently, and I think that that's correct.
That's unfortunate, but I guess it's a reality. That's why we have to really be careful. Any major accident in autonomous vehicle on the road will set back the technology a long time.
And this is probably a good time for me to intercept. This is really outstanding, excellent discussion between the professor in Singapore and professor in Oxford, both Professor Nick and Professor Ang. I'm really impressed. In fact, a lot of the discussion makes a practical sense, good deployment experience. And in fact, what I see is that this is going to go a long way in terms of how we can research good outcome and bring that quickly to the industry. And more importantly, as the different laws are put in place, we're going to see that the technology needs to get closer to the man in the street, and more importantly, to see how we can make things happen. Thank you very much again, Professor Nick House and Professor Marcelo Ang. We really appreciate your sharing here, and I'm sure the audience will have taken away lots of insights